Hello friends, welcome to video lecture on fluid mechanics. In the today's session, we'll learn about the fluid dynamics. So under this fluid dynamics, we'll cover these points: forces acting on a fluid in a motion, Euler's equation in Cartesian coordinates, expression of Bernoulli's equation. Let us see first of all what's about the meaning of fluid dynamics. So dynamics of fluid flow is the study of fluid motion with the forces causing flow. The dynamic behavior of the fluid flow is analyzed by Newton's second law of motion, which relates the acceleration with the forces. The fluid is assumed to be incompressible and non-viscous. So let us start with the equation of motion. So according to Newton's second law of motion, the net force Fx acting on a fluid element in the direction x is equal to mass m of the fluid element multiplied by the acceleration ax in the x direction. So mathematically we can just write in this way: according to Newton's second law of motion, F equals to ma. So this suffix x indicate the direction x. Okay, now in the fluid flow the following forces are present. So Fg is nothing but gravity force, Fp indicates the pressure force, Fe indicate the force due to viscosity, then Ft indicate the force due to turbulence, Fc indicate the force due to compressibility. Now from this equation the net force Fx is nothing but addition of all these forces acting along the x direction. So Fgx plus Fpx plus Fvx plus Ftx plus Fcx. Now when we neglect this force due to compressibility, the resulting net force, that is Fx, is nothing but Fgx plus Fpx plus Fvx plus Ftx. In this way you can get this relation. Okay, so this equation of the motion is known as Reynolds equation of motion. So for this one, from this equation, if I neglect the turbulence force, that is Ft, okay, then the resulting equation of the motion is called Navier-Stokes equation. Now from this, if I neglect the force due to viscosity, then this equation is known as Euler's equation of motion. Now we'll just see the relation for this Euler's equation of motion. So this is equation of motion in which the forces due to gravity and pressure are taken into consideration. This is derived by considering the motion of fluid element along a streamline. So here the that actually element is considered here for the study. Okay, so consider the streamline in which the flow is taking place in s direction. So here is that s direction is shown. Okay, now consider the cylindrical element in this way: cylindrical element of cross section dA and the length ds. The forces acting on the cylindrical element are, so first one is nothing but the pressure force PdA in the direction of flow, the pressure force P plus dabba P by dabba S into ds into dA. So this force opposes that motion or opposite to the direction of flow. Then weight element, that is rho g dA, here the rho g dA ds. So this indicates the weight of this element. Okay, now let theta is the angle, this theta is the angle between the direction of flow and the line of action of the weight element. The resultant force on the fluid element in the direction of S must be equal to the mass of the fluid element multiplied by the acceleration in the direction S. So for that, if you just say here the pressure force in the direction of the flow with us PdA. Now if I consider the component of this weight element along this along this line, and if you just if I consider the perpendicular to this one, so here we can get the cost component of this weight element, and here we can get the sign component of this element. Okay, now so PDA, opposite of this PDA, we can get the component of this one, P rho, this one rho G dA into ds. The component of this one is nothing but the cos component. So rho G dA ds cos of theta. In this way you can get that uh, component in the direction of theta. Okay, now if you just see this component is in opposite direction, that's why the negative sign is given here. Also this is also in the negative direction or in opposite direction of this flow, so the minus sign should be given for this one also. So this should be equal to rho dA ds multiplied by as. Okay, so already you have seen here the resultant force on the fluid element in the direction s must be equal to the mass of the element multiplied by acceleration in direction s. So acceleration in the direction s we have considered for that as as. And what's about this one? This indicate the mass or here okay, this one rho dA ds. Okay, that term indicate the mass of the element multiplied by acceleration in the direction s, that is as. Now where this as is the acceleration in the direction s, and what's about the acceleration? Acceleration is nothing but the rate of change of velocity with respect to time. So it is the function of s and t. So where this v is the function of s and t. Now just see here, we can just adjust this one in this way. So dabba v by dabba s into ds by dt plus dabba v by dabba t. So what's about the meaning for this one? Ds by dt is nothing but rate of change of displacement with respect to time. So we can get that as v. So v into dabba v by dabba s, this term will remain, and next term will as it is. Okay, so what's about the next one? For steady flow, we know this one dabba v by dabba t must be equals to 0. So what we get for this one as? So as is nothing but only this term will remain. For the steady flow, this term must be equals to 0. So here we can get v into dabba v by dabba s. Now substituting the value of as in equation number this one, equation number 2, and simplifying the equation, we can get in this way. So this term will remain as it is. Here we have to replace this one as by this term. If you look towards the right side of this one, rho dA ds multiplied by this as is nothing but this term v into dabba v by dabba s, in this way. So what's about towards the on this side? This side we can just write in this way. This term is written rho g dA into ds into cos of theta, this term as it is. So multiply by this term to inside term. So here p dA minus p into dA, that term get cancelled, and only this term will remain, dabba p by dabba s into ds into dA. This term is written here. Okay, now if you just see in the next step, if I divide by this one p rho into dabba, rho into ds into dA, this term to entire this relation. Okay, if I divide that rho into ds into dA, means only rho will remain here, and that ds dA term get cancelled. Here in this case rho dA ds get cancelled, so here the rho dA ds get cancelled. Now just see the remaining part only right here. So we can get here minus dabba p by dabba s, and here 1 upon rho minus g into cos of theta equals to, from right side we just see this term get cancelled. Okay, so whatever the remaining part, just write that towards the right side, v into dabba v by dabba s, this term only remain. Okay, now just take all the terms towards the one side, and again if you just see here cos of theta, you just simply focus on this small portion, so this is nothing but the length of that fluid element. Okay, this indicates the length of the fluid element, and this length is nothing but the dz. So cos of theta is nothing but the adjacent side, that is dz by ds. In this we can get for that cos of theta. So pick up this term here and just substitute here. So this can be modified in this way: 1 upon rho into dp by ds, and then we can get here g into, for this one, cos of theta is nothing but the dz by ds plus v into dv by ds. Okay, so for the entire element, actually these things are written here. That's why the dabba term is replaced by d. So in this case, if you just see here, if I take this ds as common, so ds actually becomes 0. So here we can get dabba p by rho plus this one g into dz plus v into dv. Okay, so this equation is known as Euler's equation of motion. So let us start the Bernoulli's equation from the Euler's equation. So Bernoulli's equation is obtained by integrating the Euler's equation of motion. So whatever this actually terms available with us. Okay, if I just apply for the entire element, entire fluid element, then we have to just integrate every term. Okay, now if I integrate the first term, second term, third term, okay, third term, then towards the right side we can get the constant term. Okay, now see the integration of this one. So here we can get the p by rho. So integration of this dp is nothing but the p divided by rho. This term will remain as it is. Integration of this dz, here the g becomes constant. Okay, so integration of dz is nothing but the z plus integration of this v is nothing but the v square by 2 equals to constant. So here this one g term we have taken as common from this one, and if you just see here, p divided by rho g plus z plus this one v square divided by 2g will come here and equate with the constant term. Okay, so what's about this one? So this is nothing but the Bernoulli's equation, in which the first term is nothing but the pressure energy per unit weight of fluid, or this is known as pressure head. Okay, so this term is nothing but the kinetic energy per unit weight or kinetic head. Next one is nothing but the potential energy per unit weight or potential head. So in short, we can just say this is the pressure head, kinetic head, and potential head must be constant. So assumptions while deriving that Bernoulli's equations are in this way: the fluid is ideal, that is viscosity is 0, then the flow is steady, next one the flow is incompressible, next one the flow is irrotational. Now we'll just see some of the numericals based upon the whatever the points we have discussed related with this Bernoulli's equation as well as Euler's equation of motion. Okay, so here is the problem in front of you. Water is flowing through a pipe of 5 centimeter diameter under a pressure of 29.43 Newton per centimeter square and with the mean velocity of 2.0 meter per second. Find the total head or total energy per unit weight of the water at a cross section which is 5 meter above the bottom line. So here the diameter of the pipe are actually given in the problem. Just write down the given data first of all. So here the diameter of the pipe with us 5 centimeter, then pressure is given 29.43. okay, so next one the velocity is given 2.0 meter per second, then next one z. Find the total head or the total energy per unit weight of the water at the cross section which is 5 meter above the bottom line. So value for the z with us 5 meter. Okay, so total head is nothing but the addition of pressure head plus kinetic head plus datum head. Okay, now get the one by one value. Pressure head just calculate separate, then kinetic head, then datum head. Okay, so pressure head we know the formula for the same, P divided by rho g. So value for the pressure with us 29.43 Newton per centimeter square. Okay, given. So convert that into meter by just multiplying to this term by 10 raised to actually that 10 raised to minus 4 term actually in denominator. Okay, so that actually comes in numerator in this way. So you have to multiply by that term by 10 raised to plus 4. Okay, so what's about the rho? So rho indicate the density for the water. We know that equals to 1000 kilogram per meter cube. We know a density for the water 1000. What's about the value for the G? 9.81 with us. Okay, now after doing calculation we can get the 30 meter. So what's about the kinetic head? We know this formula, v square divided by twice G. V square, the velocity with us 2 meter per second. So pure of this one, 2 multiplied by 2. So what's about the this one? We know the value for the G, 9.81. Substitute everything here and get the value for the kinetic head. So kinetic head, after doing calculation we can get 0.204 meter. So total head is nothing but addition of this pressure head plus kinetic head plus datum head. Okay, so substitute every term here and do the calculation. At last we can get the total head or the total energy per unit weight of the water at a cross section. We can get as 35.204 meter. So let us discuss about the next problem. A pipe through which the water is flowing is having diameters 20 centimeter and 10 centimeter at the cross sections 1 and 2 respectively. The velocity of the water at section 1 is given 4 meter per second. Find the velocity head at section 1 and 2 and also rate of discharge. First of all, write down the given data. So according to that, first of all, draw this diagram. So diameter d1 with us 20 centimeter. So at section 1, diameter with us 20 centimeter, as well as the velocity is also given, that is 4 meter per second. Here the velocity is given. Velocity of the water at the section 1 is given 4. By mistake here 40 written, but here actually 4.0 meter per second the velocity with us. Okay, so from this diameter, first of all calculate the value for the area. So area corresponding to this section number 1, that is A1 equals to pi by 4 into d1 square. Substitute the value for this diameter here. Do the calculation, we can get the area A1 equals to 0.0314 meter square. After that the velocity with us, that is 4 meter per second, then the diameter corresponding with the this one section 2 with us 10 meter 10 centimeter given. Okay, so consider that also in meter as 0.1 meter. So from this calculate the area. So the diameter with us substitute here pi by 4 into d square. Okay, so after doing calculation you can get the 0.00785 meter square. Now get the velocity head at the section 1. We know that relations for the calculation of the velocity head. So v1 square divided by twice g. v1, the velocity at cross section 1 with us 4.0 meter per second. Okay, so 4 multiplied by 4 divided by 2 into g means here 9.81. After doing calculation you can get the velocity head equals to 0.815 meter. Now get the velocity head at the section 2. So for that we know this relation, v square v2 square divided by twice g. We know the continuity equation. So apply that continuity equation at 1 and 2 section. Okay, so a1 v1 equals to a2 v2, this relation with us. So from this we can easily get the value for the v2. So a1 v1 divided by a2. So what's about the a2? A2 indicate the area at the cross section 2. So substitute the value for this one here, and a1 v1 v1. So a1, this value with us, v1 with us. Okay, so substitute here, do the calculation. We can get v2 equals to 16 meter per second. Then the velocity head at the section 2, by substituting the value of v2 and g, we can get 83.047 meter. Now rate of the discharge or rate flow, we can just get by using this relation. Q equals to a1 v1 or a2 v2. Just substitute the value for a1 here, v1 here. Okay, and do the calculation. We can get as 0.1256 meter cube per second. So also we can get in terms of the liter per second by multiplying 10 raised to plus 3 to this term. So we can get 125.6 liters per second. Now see the Bernoulli's equation for the real fluid. The Bernoulli's equation was derived on the assumption that the fluid is inviscid. Inviscid means non-viscous and therefore frictionless, but all the real fluids are viscous and hence offer resistance to flow. Thus, there are always some losses in fluid flows, and hence in the application of Bernoulli's equation, these losses have to be taken into consideration. Thus, the Bernoulli's equation for the real fluids between the points 1 and 2 is given as, so this is the Bernoulli's equation with us. If we consider the loss, we have to consider this one in between the points 1 and 2. So Bernoulli's equation we can get for the real fluid in this way: P1 by rho g plus V1 square divided by 2g plus Z1 equals to P2 divided by rho g plus V2 square divided by 2g plus Z2 plus HL. So where this HL is the loss of energy between the points 1 and 2. Now we'll just see the next problem on the same topic. A pipe of diameter 400 mm carries water at a velocity of 25 meter per second. The pressures at the points A and B are given as 29.43 Newton per centimeter square and 22.563 Newton per centimeter square respectively, while the datum head at A and B are 28 meter and 30 meter. Find the losses of head between A and B. So whatever the information given, okay, so if you just see here, this indicate the A point, okay, and this indicate the B point. Corresponding to this A point, this data available with us, okay. So ZA, PA, the pressure at point A with us, then the diameter at this point, at this cross section with us. Similarly, actually these terms available with us. Now at point A, so pressure with us 29.43 Newton per centimeter square. So just get that value in terms of the Newton per meter square, okay, by multiplying the 10 raised to plus 4 to this term, okay. Then the value for the ZA with us 28 meter. Then the value for the velocity at this point with us 25 meter per second, okay. So here the clearly mention a pipe of diameter 400 mm carries a water at the velocity 25 meter per second. So the value for the VA with us 25 meter per second. Now the total energy at point A. So calculate the total energy at point A by substituting the value of this one, PA, rho g, then VA, okay, then this one ZA. After substitution of all the values, so we can get the EA, that is the total energy at point A, equals to 89.5 meter, okay. So at point B, the value for the pressure, then datum head, then velocity, etc. This actually values with us. So we know the value for the pressure at point B with us 22.563 Newton per centimeter square, okay. So take that in terms of the Newton per meter square by multiplying 10 raised to plus 4 to this term, okay. Now substitute the value of rho g, then VB, okay, then this one G, then ZB. So ZB is given here 30 and in the previous case that ZA is with us 28, okay. So substitute everything and get the value for the energy at point A. So energy at point B. So energy at point B, after doing calculations, we can get 84.85 meter. Now look towards this one and this one. So difference between both these energies is nothing but the loss of head between the point A and B. So the loss of the energy is nothing but the energy at point A minus energy at point B. So energy at the point A with us 89.85 minus 84.85, you can get the 5 meter. Thank you. I hope that in the today's discussion, the points regarding the derivation of Euler's equation and the Bernoulli's theorem as well as the some of the numericals clears to you. Thank you.